Much more important of a subject to discuss than is the pseudoscience of general relativity is, here I have my general chemistry book written by Linus Pauling. Charles, this is page 308. The perfect gas equation. The dependence of the gas volume on pressure. Basically, it means that as a volume of gas at constant temperature goes up, the pressure decreases. So the equation can be written PV, which means pressure and volume, and you multiply those, is equal to a constant, and then the temperature constant and the moles of gas constant. It expresses Boyle's law. The law was inferred from experimental data by English natural scientist Robert Boyle, who lived from 1627 to 1691. And one of the most important things I wanted to realize here is that when a star evolves and it has all these different elements and elemental combinations and molecules swimming around in its atmosphere, a lot of them don't behave according to this perfect gas equation. A lot of the equations drawn up, they want to idealize a lot of the situations. And one specific instance where the situation isn't idealized, meaning it doesn't behave all the time in exactly the way they predict it to behave, is with NO2, nitrogen dioxide. It says there here, whereas all of the common gases such as oxygen, hydrogen, nitrogen, carbon monoxide, carbon dioxide, and the rest behave in the way described by Boyle's law, there are some gases that do not. One of these is the gas NO2, the molecules of which can combine to form double molecules of dihydrogen tetroxide, is N2O4. A sample of this gas under ordinary conditions contains some molecules NO2 and some molecules N2O4. When the pressure of the sample of the gas is changed, the number of molecules of each of these kinds changes, causing the volume to depend on the pressure in a complicated way, rather than in the simple way described by Boyle's law. So basically, if you have a container of NO2 and you pressurize it, it becomes more N2O4, meaning that more than likely that NO2 combines with itself under higher pressures. Now, another big thing I realize is that I have to write this down, is chemists these days, they wanted to make what's called standard conditions. And the standard condition applies to, Earth's atmosphere being at a certain temperature, or temperature and pressure. It's the standard conditions. It's to make a lot of the discussions of, experiments to where other scientists can say, oh, well, standard conditions. It's to make it on equal grounds. That way they can share results with each other a lot easier. Unfortunately, the idea of standard conditions made it to where they only focused on a certain set of conditions. They didn't branch off back then. They didn't branch off too much. But now what we have to do, if we're going to study gas pressure and how it interacts with itself, and especially with like partial pressures of a gas mixture, different types of vapor, pressure of water, gas volume on temperature, especially when it's near supercritical, especially when you have all that, we have to make what I would consider to be standard conditions for the internal parts of an evolving gas giant per se. Because the standard for the Earth is not universal. The standard for Earth is just us communicating with each other. But if we're going to understand the kind of pressures involved in the interior of Jupiter, the interior of Neptune, the interior of Uranus, the interior of Saturn, and a lot of the other less evolved stars, such as, the exoplanets, we're going to have to develop conditions to where they can apply to each stage of star evolution. Say this will be standard for an M-type dwarf star, which is a red dwarf, as it forms its core. Or this is standard to the internal parts of the mid-atmosphere of a gas giant, say Jupiter-sized object. And this is standard for a Neptune. You see what I'm getting at? Because a lot of the gases, they behave very, very differently, and especially when they're undergoing chemical reactions. So say you have, a vat or some liquid hydrogen, it's gonna react differently per the element that it's around. Plus, especially things like fluorine, which are very, I think it was called electronegative, meaning they steal electrons from other atoms. And I want to talk about that as well. So keep all this in mind. A lot of the understanding how a star evolves has to do with gases, but at the same time, you're going to run into the standard conditions a lot. And it says here, it is customary to refer to the volumes of gases to conditions of temperature 0 Celsius and pressure 1 atmosphere. A sample of gas is said to be reduced to standard conditions when its volume is calculated at this temperature and pressure. So, if we're going to talk about the stars, we have to kind of look at huge volumes of work where they try to reduce everything into standard conditions. And standard conditions are very, very poor in regards to being able to apply that to stellar evolution. Because stellar evolution is like a big forest, like the Amazon jungle. And standard conditions is just like this little air conditioning building sitting in the middle of it. Oh, standard conditions, let's go to the air conditioning building. But then you have star evolution, this big thing, can't be fit inside of that tiny little air conditioning building, surrounded by many thousands of square kilometers of forest. But basically that really sums up this talk. And I stress reading this stuff because I want to get to the nuts and bolts of star evolution. And I think the best way to get to the nuts and bolts of it is to overview a lot of chemistry books. Really big, thick chemistry books. Because that is the bread and butter of stellar evolution. Alright, today is July 14th, 2015.